Good afternoon, everyone. Thank you for attending. In this talk, we'll present our recent study and a comparison between the inverse scattering series free surface multiple elimination algorithm with the industry standard surface multiple related multiple elimination algorithm SRME plus energy minimization adaptive subtraction for isolating for removing isolated free surface multiple and for removing interfering free surface multiples. So basically, we would like to deliver the following message from this presentation. To remove the isolated free surface multiples, both the ISS method and the SRME method can be effective. However, for removing the interfering free surface multiple, we suggest the ISS method. And when it is not clear if a free surface multiple is interfering with primaries, it is prudent to choose the ISS method. So that's the main method we want to deliver from this presentation. Now let's start our discussion. So earlier this morning, Professor Weglein, in one of the Professor Weglein presentation, we stated that the relationship between the removing multiple and using multiple are not adversary but complementary. And both aspects are important and worth pursuing and should be encouraged. And in this study, we work on the method for the removing multiple. In specific, we study the method to remove free surface multiples that are isolated and interfering. And for your information, later in this meeting, following this presentation, we will discuss the analogous issue of removing internal multiples that are isolated and interfering. And in particular, following this presentation, my colleague Yang Zhou will discuss the removing of isolated internal multiples versus removing the isolated interfering internal multiples by the ISS internal multiple attenuation algorithm and the elimination algorithm. Now back to this subject of this presentation. So among the methods to remove the free surface multiples, we choose to study two methods. One is the inverse scattering series method. The other is the SRME method. The reason why we choose to study these two methods versus other methods such as stacking, FK filtering, Qiang, and redone is both of these methods are do not require any subsurface information to be effective, and there are also differences between these two methods. The SS free surface multiple elimination algorithm provides free surface multiples with accurate time and accurate amplitude in principle, whereas the SRME method in principle predicts the free surface multiples with only approximate time and approximate amplitude. And we would like to examine the effectiveness of these two methods under different circumstances. For example, by different circumstances, we mean to remove the free surface when it is isolated, and to remove the free surface when it is interfering, and to remove the free surface when it is not clear if it is interfering or not. And we would like to, through this examination, we provide a guide for when each of these methods can be an appropriate choice in your multiple removal toolbox. So now let's first provide a brief description of these two methods. We would like to focus on the equations used in these two methods to predict the free surface multiple and what the input and output of these two algorithms. First, let's look at the ISS method. For the ISS free surface multiple elimination algorithm, the input data here we're following the notation used by the developers of this algorithm, where we use D1 prime to represent the input data, where the variables kg, ks, omega is a Fourier transform from the xg axis and time, where the xg axis is a space location of the receiver and source, time is a time variable. And what the prime here means the input of this data has gone through the process of removal of reference wave, where we have the plots to show the reference wave and without any ghosts. And given this input D1 prime, the equations on the second row of this table predict the free surface multiple from the ISS method. Let me first explain the variables in this prediction equation. So first, A omega is the source signature. The epsilon g and epsilon s is the receiver depth and source depth, respectively, of the seismic experiments. And Q is the obliquity factor, defined as the square root of omega over C0 squared minus K squared. And N is actually a positive integer starting from number 2. And each dn prime performs two functions. It eliminates the n-1th order free surface multiple, and it also alters all high order free surface multiples to be prepared for their removal. And the sum of this d2 prime plus d3 prime up to the dn plus 1 prime, this sum of this prediction term provides the free surface multiple predictions with accurate time and accurate amplitude but in opposite polarity compared to the actual free surface multiple for the free surface multiple up to the nth order. That means depending on their goal of how many orders in your you want to remove in your data. Let's say you want to remove up to the third order free surface multiple. All you need to calculate is the d2 prime, d3 prime, and d4 prime. So that depends on how many terms you will need to be calculated in this prediction term. And please remember, this prediction term, as we stated here, gives the accurate prediction of the free surface multiple in time and amplitude. So to obtain the output, which is without the free surface multiple, we can directly apply this prediction to our input data without any adaptive procedure because of this accurate prediction. Now for the SRME method. So given the same input without reference wave and ghost, here this equation shows the convolutional operation of the prediction of the free surface multiple in the SRME method. And because this SRME prediction of the free surface multiple provides a approximate amplitude prediction and approximate time, and to obtain the output without the free surface multiple, an adaptively subtraction procedure is required, usually with an energy minimization to obtain the output. So we see that this adaptive subtraction is actually a part of this method that's aiming to fill the gap between this approximate prediction and the actual free surface multiples. And we understand much of the effort and time of using the SRME methods to remove free surface multiple is devoted to the adaptive procedure. And instead of the energy minimization criteria, a lot of different norms can be proposed. Here we would like to focus on the prediction part of these two algorithms to see comparing these two methods in terms of the free surface multiple prediction. Here we explicitly show the equations used in this method for predicting the free surface multiple. We can see for the SS method is in the Fourier domain, whereas for the SRME method is in the space frequency domain. And in our annual report, we have arranged them to the same domains for either conversion. For interested audience, so you can refer to our annual report. Now let's look at a numerical comparison between these two methods to remove the free surface multiples under different circumstances. So first, let's look at the model we designed for this test. Here shows the 1D subsurface acoustic media for our test data generation. We have two reflectors at 300 meters and 750 meters. And based on this model, we generate our test data, which is for the primary due to the first reflector here. And we generated a primary due to the second reflector. And then we generate a first order free surface multiple bouncing between the first layer. Here. Highlighted by this red. And we can see the two green line, which represents the primary, and the red line represents the free surface multiple. Actually, the free surface multiple is interfering with the second primary around the offset 750 meters. So given this input data, we put the input data to the two prediction algorithm and compare the prediction of the free surface multiple to the actual free surface multiple in the data, which the actual free surface multiple in the data will serve as a benchmark to evaluate our accuracy in this prediction of these two algorithms. So let's show. So this slide shows the comparison between the actual free surface multiple on the left, the ISS free surface multiple prediction in the middle, and the SRME free surface multiple prediction on the right. And to look into more details of this prediction comparing with this actual, let's extract several traces at different offset. Let's say we want to extract 3 traces at 100 meters offset and compare them together, and extract the other traces at 500 meters, compare them together, and at offset 1,000 meters and compare them together. And the next slide, I will show the comparison of it. So figure on the left shows the trace comparison at 100 offset. The middle is 500. The figure on the right shows the 1,000. And the black line it represents the actual free surface multiple pointed by the actual black arrows. The red line represents the ISS free surface multiple prediction pointed by these red arrows, whereas the green line represents the SRME free surface multiple prediction pointed by these green arrows, where we can see this red line and green line, black line overlap. So, which says the ISS free surface multiple predicts the free surface multiple with accurate time and accurate amplitude, and agrees very well with the actual free surface multiple in our data, whereas the SRME provides the approximate prediction. So next, let's show the comparison between the actual data and the results after these two methods. In other words, last slide we showed the prediction of these two algorithms comparing with the actual free surface multiple in the data. Next, we will show the results after the free surface multiple prediction of this from these two methods to the actual free surface primary in the data, where the actual primary in the data again will serve as a benchmark to evaluate the results from these two algorithms. So this figure shows the actual primary. Figure here shows the results after the ISS method, and here shows the results after the SRME plus adaptive. And for either comparison, I plot the actual primary and the actual free surface multiple in the data on the left for either comparison. So next, let's first focus on the results after the ISS free surface multiple elimination. When we're comparing these three plots, and as highlighted by this red dashed line, we can see. So in the SS results, the free surface multiple has been nicely removed, including the primaries where it interferes with the primary. It also preserves the primary in the ISS results. Next, let's focus on the SRME results. Then here we show again with the approximate prediction of this multiple from the SRME method, but this approximate prediction combined with the adaptive can also successfully remove the free surface multiple by the SRME method, as highlighted by this red dashed line. However, when we examine the results, especially the primary with actual primary, we can see at the part of the primary that interfere with the free surface multiple is damaged, as highlighted by these two black circles. Next, we do a trace comparison at this interfering zone, where we compare this this results from these two algorithms with the actual primaries. And here, this black line and almost overlap with the red line, where we can only see the red line, whereas actually the black line represents the actual primary, where this red line represents result after the ISS method. We can see the ISS method can preserve the actual primary very well, whereas due to this adaptive procedure, that the SRME method can, the primary is damaged due to this adaptive procedure in the SRME method. So from this example, we show that to remove the isolated free surface multiples, both methods can be effective, as we can highlight here, where this isolated free surface multiples are both removed by both methods. However, if we want to remove the interfering free surface multiple, the ISS method is suggested because the adaptive procedure in the SRME method can damage our primary, whereas the ISS methods, without depending on the adaptive procedure, can preserve the primary very well. And when it is unclear if a free surface multiple is interfering with the primary, it is prudent to choose the ISS method. Now we have discussed the free surface multiple prediction, free surface multiple removal, and the different circumstances. The natural question is, and also earlier from Professor Weglein's presentation, he mentioned both the ISS free surface multiple algorithm and the internal multiple elimination algorithm are model type independent. By model type independent, we mean the algorithm remains the same independent of the Earth model for acoustic, elastic, and inelastic. So in this specific study, we would like to see how the ISS free surface multiple performs by introducing the absorptive property in a media. So to show this, we use the same model as we see in the last test. The only difference is we introduce some absorptive property in the media for our data generation. And similar to the last test, we generate two primary and one free surface multiple, as highlighted in these slides. And we first do a comparison between the two prediction results with actual free surface multiple in the data. Here, figure on left shows the actual free surface multiple, the ISS free surface multiple prediction, and the SRME free surface multiple prediction. And again, to look into the details, we extract traces to do a trace comparison at 100, 500, 1,000 meters. And the same to the previous test, we can see the ISS methods in the presence of the absorptive property can still effectively predict the free surface multiple with accurate time and accurate amplitude, whereas the SRME method is approximate prediction. This red overlap with the black, so it's nicely agree with each other. And this green line represents the SRME prediction. Now let's look at the results after these two algorithms and comparing with the primary in the presence of absorptive property. Again, the three figures on the right show the actual primary results after the ISS method, the results after the SRME plus adaptive. Again, for easy comparison, I show the actual primary and free surface multiple in the data for comparison. Same to the last test, we can draw the same conclusion here in the presence of absorptive property. See, the result by the ISS method can be the free surface multiple are removed. See, there's one even here. The free surface multiple is removed, and the primary is nicely recovered. See. Then let's see the SRME method, then the free surface multiple is removed with this approximate prediction combined with adaptive, and the part of the interfering primary is damaged by this adaptive procedure, as highlighted by these black arrows, black circles. And we can also do a trace comparison around this interference zone. And again, we see the ISS results nicely preserve the actual primary because the black line represents the actual primary, the red line represents the result after the free surface multiple, and the black and the red overlap. And whereas this green line represents the results after the SRME plus adaptive, and this adaptive can easily damage this primary where it interferes with the free surface multiple. And the same conclusion we can draw as this last case in the presence of absorptive to remove the isolated free surface multiple. Both methods can be effective. Let's switch height here. And to remove the interfering free surface multiples, the SS method is suggested. And it is prudent to choose the SS method where it is not clear if a free surface amount is interfering with the primary. Now, so we draw the same conclusion. The SS free surface multiple elimination algorithm remains its effectiveness in providing the free surface multiple elimination algorithm with accurate time and accurate amplitude. Now let's look at the summary. We mentioned there are prerequisites of this ISS free surface multiple elimination algorithm, and early this morning, my colleague Professor Weglein and Qiang all talk about the prerequisites. Especially for the ISS free surface multiple elimination algorithm, the prerequisites are the wavelet estimation A omega in the equation, and the removal of reference wave, and the removal of ghosts. And the significance of satisfying those prerequisites is twofold. One is satisfying these prerequisites will promise the effectiveness of the ISS free surface multiple elimination algorithm. And the second is effectiveness free surface multiple removal will ensure the delivery of all subsequent seismic data processing objectives, such as the ISS internal multiple attenuation and elimination, and the ISS and the imaging, including both the ISS method and the STO-C3 method. So here we list the, because the prerequisite is so significant, the considerable amount of efforts and time has been devoted to work on providing those prerequisites in practice. Here we list only a sample of the reference that for these prerequisites. And for sure, there are people outside of this group working on like wavelet estimation, removal of reference wave, and deghosting. And we recognize their work when developing our own methods based on this, mainly based on the green serum methods. And we refer you to follow up this detail reference for further details. And because here we are discussing the green serum method to provide those prerequisites, we thought it would be useful and helpful to show one example that actually shows the green serum method can effectively provide the prerequisite of the ISS free surface multiple elimination algorithm. And this example is from the thesis of Dr. Jifeng Zhang, who is one of the pioneers who actually developed this green serum method to do the wavelet estimation, the removal reference wave, and the deghosting. And what he did is using this model shown here, where on the top there is a free surface multiple, and there is one reflector here. Using this model shown here, he first generated data that all the available events in this experiment, like the reference wave, the ghosts, the free surface multiple, where we only plot the reparts of this free surface multiple first order, and of course one primary. Because we have only one reflector, there are no internal multiple in this specific example. And after he generated this data, he used the Green-Serum method to remove the reference wave and to do deghosting. And then this result from this Green-Serum method, which includes the free surface multiple and primary, which is D1 prime, as we noted here, is as the input of the free surface multiple elimination algorithm. If the reference wave removal and deghosting is not effective, then the ISS method won't be effective. Then let's look at the results. First, here shows a trace comparison between the input data. We use D1 prime, represents in this trace plot by this solid line, comparing this input with the result after the ISS free surface multiple elimination algorithm, which represents by this dashed line in this plot. The result is obtained by adding the first prediction term from the ISS free surface multiple elimination to the input data. And when this first prediction term is added to the prediction, two things happen. One is the first order free surface multiple is eliminated, as highlighted by this red box, where again we can see this in the results, which is represented by this dashed line. It's got flat, whereas this first order free surface multiple is removed. And then all the high order free surface multiple is altered and prepared for the removal by the subsequent terms D3 prime and D4 prime, like as highlighted by this red box. And of course, the primary is nicely preserved. Now here, the last example shows that based on the Green-Serum, the methods can be developed to effectively remove a reference with removal and deghosting, which can provide the prerequisites for the ISS free surface multiple elimination algorithm in practice. And in the end, I would like to show you one last example, which is the first ISS free surface multiple elimination algorithm field data test, marine data, carried out by this Paulo Carvalho and Weglein. And here, figure on the left shows the results before multiple subtraction short gather, and the figure on the right shows the multiple subtraction results using this ISS method. And then he also compared this ISS method with the FK filtering, where we can the figure on the left shows the result before the multiple subtraction. The figure in the middle shows after multiple subtraction using the ISS method. The figure on the right shows the results after multiple subtraction using the FK filtering. The conclusion in this test is the ISS method is more effective in removing free surface multiples where without damaging the underlying primaries, whereas this FK method is not as effective as the ISS method in that regard. So with that, I would like to remind you the main points from this presentation. So for removing of the isolated free surface multiples, both the ISS method and SRME method can be effective. However, to remove the interfering free surface multiples, we suggest to use the ISS method. And when it is unclear if a free surface multiple is interfering with primaries, it is prudent to choose the ISS method. And one last point to emphasize the importance of effectively removing free surface multiple is we should keep in mind that removing free surface multiple is only one step, actually one early step in the seismic data processing chain. And an effective removal of free surface multiple is a prerequisite of all subsequent steps. For example, following this presentation, my colleague Yang Lizhou is talking about the ISS internal multiple attenuation. An effectively removal of free surface multiple and a preserve of primary is a prerequisite for the ISS internal multiple to be effective. So we wanted to, as best as we can, to remove the free surface multiple and preserve the primary. So with that, I would like to thank you for your attention, and your comments and questions are welcome. Thank you very much.
concrete example, how do you generate this? Final difference or integral method?
That's a good question. So we generate using, because this is a 1D model, we have the analytical form for each event. So we, based on the analytical form, we can.
Integral, okay.
Yes, yes, yes.
Did you ever test anything using the data set to generate final difference?
No, we haven't had a chance to test it yet in this study, but that will, like for the final difference method, because it's final difference method, it will generate every event available in the experiment. Since we have the free surface, it will have the ghost and like a reference wave. And we, in order to put this data into the free surface multiple elimination, we have to first go through the remove reference wave and the deghosting, just like Jingfeng Zhang's example shown. He first goes through the remove reference wave and deghosting, and then put the output from the last step to the ISS free surface multiple elimination. Okay. Yes, thank you. Yes.
So, can you explain to me conceptually where the equation for the SFME, how is it related to the inversion scatter series? What part of the series represents this step? Possible.
You mean?
I mean, we are talking about inversion scatter ISS and how you dive in and take the parts which are interesting for a particular problem. So I'm wondering how that was one of the first equations you showed. Yeah, like here. How is this related to the inversion scatter series? What part of the series it is? What terms? Can you describe that conceptually?
Professor Weglein is talking about the data, communicate the data to the ISS jobs, including the free surface and internal. Here, conceptually, here's the data, and here also the data. So the data is multiply the data to. Yes.
I'll put it on the board.
Okay.
Oh.
Too much for lunch. Thanks. No. It's on. Is it on?
It's good.
It's on? Good, thanks. Okay, so what I'm going to do is I'm going to put down two situations. One where there is no free surface, yes, and one where there is a free surface, yes. And so assume that there's a water here which is infinitely high, yes. And then there's Earth. Yes. And then imagine here there's a water which is has a top. Yes. And then has the same Earth. Okay. In this case, I'm going to let's say this was the problem, yes? We're going to treat each as though it was the problem and look for the difference, yes? So if this was the problem, I will choose a whole space of water as reference, yes? So the G0 here will be G0 direct, what we call, or G0D. In other words, just a direct, in a homogeneous whole space, the reference is just, here's the source, here's the receiver, it just goes like that, yes? And then the V will be this, the Earth. The perturbation will be where the water ends and Earth begins, yes, some function. In this case, the reference will be, G0 will be G0 direct plus G0 FS. Because here the reference will be like a vacuum, let's say, or air, and then water, yes? That's the reference. And so the reference will have a piece that does this, like G over there, and a piece that does this. And then it has the same V. In other words, different reference, but the same V, yes? One with a water top, one without. So in the forward series in each case looks the same, except what G0 means. In other words, it'll look like G0 plus G0 VG. I'm talking the forward now. The forward series, yes? G equals, yes? So in the case of the infinitely high water, there's only two kinds of events that return: primaries and internal multiples. There's no free surface multiples. There's no ghost. And we'll assume we took the reference wave out. This will be the reference wave. Here will be just a direct wave, yes? So here this is going to be G0D without a free surface, yes? So we'll call that without free surface. The G with a free surface will have the same, except the G0 will have two pieces. Okay, this is the forward. Now the real interesting is the inverse, which I'll do in a second, yes? I'm just trying to show you the forward first to get a sense. So this one, G0D plus G0FS, and then every one of these is 2. In other words, with the free surface, yes? Is G0D plus G0FS V, and then the same thing, yes? And then, in other words, every place you have, right? It's just a different reference Green's function, the same Earth. So the first thing is, this world has different events than that. The events that are here that are not there are, there's a reference wave that's different, yes, has that, and it has ghosts. This is ghost. In other words, it has two pieces, one that's coming, and here's a source, and one that's doing this. You follow? In other words, this guy is direct to V, down. This one goes up and then down, yes? This guy is a ghost. In other words, from the source up. The same on the receiver side, yes? So there are, when you get to the next term, so this first one is just ghost making, yes? The next one has a G0D plus G0, I'm talking forwards so far. In the middle, the same 2 here, another V, okay? You follow? G0D plus G0FS. I got 2 now. I got this in the middle. That's make a free surface, okay? Because this guy will go, let's say this one will go down, hit a V. This one says, from hitting, go up to the free surface and then down. That's a free surface multiple. So, and this one just goes between 2, you know? And so, this gives you, so the purpose here is, in the forward series, G0FS, in the forward series, G0FS is the extra piece that's here that's not here, yes? G0FS creates the events that are here and not here, meaning ghosts and free surface multiples. So if you start with this situation, your data has primaries and internal multiples, and it's got issues, and G0D has to deal with them, has to get rid of internal multiples, yes? Has to, after it does that, has to do depth imaging, nonlinear AVO, G0D, that's its job, yes? Over here, so you have a new set of issues on the inverse. It has to remove ghosts and free surface multiples that don't exist here. Who made them? You made them. You made them. You better fix them. In other words, you are the extra in the forward series that made those events. In the inverse, it's got an issue to deal with them. G0D can't deal with them. It deals with issues like this. You understand? Issues with internal multiples and primaries. So let me show you explicitly now in the inverse how that works. In the inverse, so I just want you to accept that G0FS is going to have something to do with removing issues that it helped make, because that's the only possibility, because G0D, it just knows how to do this, yes? Okay, so just let me write down one or two, because okay, I'm going to write down G0, V1, G0, okay, equals the data. And this data is going to have the reference wave removed, no reference, but yes, ghost still, ghost. Because what we're doing here is, this is, I should have Paulo Carvalho here. This is his thesis, okay? This is, we were together, you can tell. So, this is the first term in the inverse series, yes? The second term is G0, V2, G0 equals minus G0, V1, G0, V1, G0. Okay? I'll just give you a sense of how it works from here, okay? What happens is the following. We are in the case where there's a water top, yes? There's a water top. So the G0 has two pieces, G0D plus G0FS, and G0D plus G0FS. All the outer ones have that, and the inner one has it. Yes, they have two pieces, the inverse. What the first step that Paulo Carvalho does is, this is done in the Fourier domain. In other words, in the space domain, these are integrals over the variables of V1. Yes. In the Fourier domain, it's products. It becomes products of, yes, it's convolutional and then becomes products. So what happens is, the first step that Paulo does is he removes that G0, which is just a division in the Fourier domain, and replaces it by G0D everywhere, the outer ones. That deghosts. In other words, replace this by G0D, by a simple division by it on both sides, yes, and multiplying by G0D. So you're ending up with G0D V1, G0D, which is what we call D prime in the literature, the deghosted data, yes? You follow? By removing the two piece and removing the two piece and replacing it by the direct, yes, on both sides. Now, the problem, don't be upset, Paulo, but if you say, if Paulo showed you how to deghost, why are we doing Green's theorem? Yes? Here's the reason. This method is depending on knowing the depth of the cable. Okay, the depth of the cable, in other words, it's taking two measurements, if you like, zero and the cable, yes? Zero pressure, and here. That's works perfectly if you know the depth of the cable perfectly. If you don't know the depth of the cable, that's unstable. Okay, there's a division. Okay, if you have two measurements at one depth, like Green's theorem gives you, in other words, you need two things to do up-down separation. You give me two, okay? I'd rather have two here. You understand? Two here gives you stable. One here and one here doesn't. Yes? So the Green's theorem is doing this. Two at the, that's why we needed the field and the derivative. Geostreamer, that kind of thing. You understand? It's for the stability of but in principle, there's a deghosting. So you could achieve it with Green's theorem and then put that in for your data, D prime. But the more important thing is, so you deghost. Everybody gets deghosted, the whole, that just takes care of the outer ones, okay? The inner one has two pieces, G0D plus G0FS. And there's, in other words, it keeps doing that. G0FS plus G0D. V1. G0FS plus G0D. V1. G0, in other words, I'm doing like higher terms so you can see what the story is. So now, how do we get isolated terms? Yes? The idea is this. In other words, the outer ones, we make G0D. Yes? The outer ones. That's deghosting. The inner ones is where, after deghosting, it has things to do. This guy is dealing with, G0D is dealing with the things that, like that, primaries and internal multiple tasks. That's, you understand? G0D, when you didn't have a free surface, the reference was G0D there. It had to deal with internal multiples and primaries, yes? So it didn't learn new tricks. And G0D is still G0D, you understand? So this guy, even though you're in the situation with a water top, it's trying to do things that it's able to do. You know, depth image, you know, internal multiple, attenuate, eliminate. So there are terms here that could be this times this. You follow? This times this. That's a coupled term. That's somebody trying to do something on primaries and internal and a free surface. What we mean by isolated is look at the series and look at terms that seem to have only one job on their mind, as if there was no other. Yes, isolated. As if the only job that that term thinks it needs to do is free surface removal. So for that, we take terms that only have this. Anything with this, we're not dropping them, we're choosing the terms that are only free surface. And so this G0FS, that's where that algorithm that Dr. Chao Ma. So where does that obliquity come? You know, that famous obliquity that's in ISS free surface and not in SRME. It comes from the G0FS. Okay, the data has it has to be put back in terms of this has to be put back in terms of data. You know, that original deghosted data, because it's a data algorithm, and that data brings in a 1 over Q, and then so the V1, in other words, this guy has like a 1 over QG, 1 over QS in the Fourier domain, okay? And so the V1 has a Q1, QG, QSD going in here. And this guy has a 1 over Q, ending up with a factor between the V1, the data, and the data of Q. That's where the data, Q data comes from. Yes? So the main point here is, you will look, isolated task is what saved us, okay? Meaning, we look for, can you look at terms in the series that seem to, on their mind, only have one issue: free surface multiple removal. That's all they want to do. Well, what about something that wants to do free surface multiple and also internal? Don't look at it, okay? Don't look at it. Then what do? After we got, thanks to Paulo Carvalho, an algorithm that was all G0FS in the middle, yes? Free surface multiple removal. In comes the data with free surface multiples. Out comes the data without. We start the inverse scattering series as if there's no free surface. Never look at coupled terms. You follow? In other words, we have transformed to this problem. So the coupled G0FS, G0D are never looked at. And we repeat it. Now look at terms that only look like they want to deal with internal multiple, not depth imaging, not nonlinear AVO, okay? Just internal multiple. Select them, yes? Anything it wants to do two or another thing by itself or internal and that, don't. Then clean up the internal multiples, make it a data with only primaries. Then go back in, look at subseries, okay? If it's not clear, I'm happy to meet with you alone.
No, it was very helpful. Yeah.
Okay, you're welcome. Okay. Paulo, you got that right? That's his thesis. You should know Paulo Carvalho's thesis in Portuguese. I don't read Portuguese. But so I have no idea what he said. Could be some bad things in there. Okay. I'm happy to follow up if you have further. Thank you. Okay. Any other questions for Dr. Chao Ma? Okay, excellent talk.